Welcome to the next video in our System Devices 2 networking series. We continue our investigation of the network layer, layer 3. So at the end of last lecture, I asked you to look into our old friend, the TTL field, the time to live field, and the new one, fragmentation. So fingers crossed that little bit of research went smoothly, so you've got a rough idea what those terms refer to, and obviously in this lecture and in the lab we're going to look at those in a little bit more detail, devise some network scenarios to see these in action. So in the last video we looked at our IP protocols, so IP version 6 and 4, we looked at subnetting and we looked at routing, how those packets are routed across our network, how that information is passed between the different routers. We saw how routing tables can be used to route our packets and how we could add manual routing rules to our networks to ensure that our IP packets take the correct path. However, you can't manually set up every router on the internet. That would be just too much fun. So we have an array of routing protocols. So protocols that allow routers to transfer routing information between themselves. So they can send each other information about what should be within their routing tables. They can update their routing tables based upon what their neighboring routers know. So as always, to see if you understood that material, a quick quiz. So what we have here is our typical Raspberry Pi system that you have in the lab. So we have our PC, a switch, our 3 Raspberry Pis and our router. But as you are aware, there is a spare port on our router, port 4. So we can use that to connect to another network. So in this scenario here, that port will be assigned the IP address 10.0.0.1 and that will be connected to a switch. And I want to connect one or more new PCs to that switch to form a 10.0.0.0 network. So a /24 network. So the question here is, what machine should assign this PC an IP address? So I'm looking to assign it an IP address from the pool 10.0.0.2 to 10.0.0.254. So within that range. So should that DHCP server live on the PC? Should it live on a Pi? Or should it live in a router? What do you think on that one? Equally, what routing rules do I need to add to my system to allow Pi 2 here to connect to that PC? So what routing rules do I need on the PC, the router, and Pi 2 to allow these two machines to communicate? So again, as always, think about what the default gateways are within this network. So obviously they're exactly the same as the ones you've seen in the lab. And what would happen if this PC was to request a connection to the IP address 192.168.100.2 in this example? Or what would happen if the Pi 2 requested a connection to this machine, which perhaps is assigned the IP address 10.0.0.2? Will it work? Do I need to add routing rules to that system? And as always, we will talk through that in the lecture review session. So you saw in the previous lecture that we're using our IP packets to transport our data across our networks. We're using the source and destination IP addresses to identify the machines on the network, and we're using those IP addresses to route our packets across the network. But always remember that these packets carry other protocols. So these packets will carry your UDP and TCP segments. And that's identified in the protocol section here. So within this 8-bit field, we have different code numbers to identify what payload we are carrying. So our IP headers will be stripped off when they're received. As we pass these packets up the protocol stack, we need to know what the data contains. We need to know what the data is. Is it a UDP packet or is it a TCP packet, for example? Some memory. So I think the value 6 for TCP and 17 for UDP, maybe? Do check those, but basically a number. So for each of the different protocols that our IP datagram may be carrying, we need to tell the receiving machine what is this data, and that's done by a number. Okay then, so our IP datagram will be carrying our transport layer segments, so a TCP or UDP segment. The size of our IP datagram will be given by this field here. So this 16-bit value will be the number of bytes in our data section. So our segment data plus this header, which is typically 20 bytes. And that will be transported across our network as Ethernet frames. However, as we saw in a previous lecture, the size of our packet is limited to the maximum transmission unit, and that is defined by our hardware in our network. And as I mumbled in a previous lecture, that is effectively defined by how much memory our routing devices have inside them. So our routers are store and forward devices, so they'll be receiving packets, they'll have to process those packets, they'll have to buffer those packets. So when we're designing such systems, we need to specify how big those packets will be, so we know how much memory needs to be on those routers, because we don't want to start dropping packets. We need enough capacity within those routers, we need enough memory within those routers, such that we can store the packets as they come in. So originally, MTU values were around 576 bytes. So that if you broke that one down in terms of your IP header, TCP header and your data sections, then you're typically looking at values shown here. So normally your IP header is around about 20 bytes, TCP header 20 bytes, and that will leave you 536 bytes of data, of payload. So if you look at the ratio of headers to data, that's not bad, that's 93%. So you've got a relatively small header compared to the amount of data you're sending. But as memory got cheaper, we've increased the MTU, and so now our network hardware can carry bigger packets, it can buffer bigger packets. So something around about 1,500-ish is what we're looking at nowadays. So again, if you took that value, again, our headers haven't changed in size, but our payload can be bigger. We can store more data for the same amount of header, so our efficiency improves. Again, as memory has got cheaper and cheaper, we have moved up to jumbo packets now. So something around about the 9,000 mark can carry approximately 8K's worth of data. So again, if you look at the ratio between headers and data, we're getting more efficient. And as we can see in the UDP header and in our IP header, the length of our segment or our datagram is defined by a 16-bit value. So in theory, you could have 64K-ish worth of packet size. So our maximum transmission unit could be up to that sort of size. So again, if you did push those levels, you're starting to see even more efficient communications because you've got so much more data compared to the headers needed to transport that data. However, there's always a trade-off. So when considering the size of your MTU that you'll be using, you need to consider how noisy your network is, what the error rate is in your network. You can imagine a scenario where you've got periodic bursts of EMI, electromagnetic interference, that will corrupt the data on your copper wires. So if you were using small packets, that may corrupt 1 or 2 packets worth of data, and those packets would need to be retransmitted. And if the time between those electromagnetic pulses was relatively large compared to the time it took to transmit those packets, then these could be safely transmitted in that period of time. However, if you have got very large packets, then that's going to take a significantly longer period of time to transmit. So you could have this scenario where you're constantly retransmitting these jumbo packets because the noise is so frequent and it takes significantly longer to transmit these packets. So every time you try to retransmit that very large packet, it's getting corrupted. So there is that trade-off. Obviously, if you have a system that is that noisy, then you've got severe problems. So typically that wouldn't be an issue, but you do have to think about the cost of retransmissions. Very large packets come with a large cost associated with that retransmission, but they do improve your network efficiency. Okay, so your MTU is defined by your hardware. The size of your UDP packet is defined by your software, and they don't necessarily have to match. You can define in software a very large UDP segment. So you could define a 64K UDP packet. So you carry the image of Bob, for example, in one UDP packet, in one UDP segment. However, the lower layers may not support such large packet sizes. They may be working on packets of 1,500-ish bytes. So therefore, what do? So your transport layer wants to use big segments, your underlying hardware can't support those, so somebody's got to do a translation between the two, and that's what IP does do for us. And that's what these headers allow us to do, that they allow us to fragment our data. They allow the hardware to break down our bigger UDP segments down into smaller IP packets. And to show that in action, we can update our UDP file transfer program. And now, rather than using 1024 byte data blocks, we can use 9000 byte blocks. We can capture that in Wireshark, and we can see here we have a UDP packet of 9,000 bytes, but that has been broken down. It has been fragmented into a number of 1,500-ish bytes IP packets. And in the lecture review session, we'll have a look at these fields here, so offset and ID. So if we go back and look at our IP header, you can see we have fragment offsets and ID identification code. And we can see how fragmentation works. Right then, so the next IP header field that we're going to look at is the time to live field, our TTL field. And we've seen that previously in one of our labs. So we saw that in the traceroute lab. So to allow the traceroute program to detect the path that a packet does take as it crosses the internet, as it goes through the series of routers that connect the networks of networks together to allow your packet to travel from one host to another host across the internet, it uses the TTL field. So initially it sets it to the value 1. Obviously that then sends that to the first router. The router will decrement that by 1, resulting in a 0 TTL value. If you do get down to 0, that packet will be dropped, removed from the network. The TTL value you can think as a def counter. So every time it goes through a router, it will be decremented to 1, and when it gets to 0, it will be dropped. If you have a nice router, it will send back an error message to you, and that's how traceroute detects how far that packet has got. So the first packet our traceroute program will send out will have the TTL value of 1, so it'll reach the first router, it will be dropped, the router sends back an error message to us informing us that it's got that far. The traceroute program will then send out the same packet, but now with a TTL value of 2, so it'll get through the first router perfectly fine. It'll get to the second router now, again reach a 0 value. So now the second router will send back an error message informing us now how far it has got. It's got to the second router, and as you probably guessed, the traceroute program keeps repeating the same process, incrementing the TTL value and recording to where that packet has got in the chain of routers before its TTL value reached 0. So there's no direct mechanism for the traceroute program to trace that path, but by using the TTL values, if your routers are nice enough to send back that error message. And we'll be looking at those in more detail in a later lab. So we'll be looking at ICMP packets. So ICMP is the protocol that allows you to send diagnostic information about what IP is doing across a network. So the Internet Control Message Protocol. But for the moment, we'll ignore that and just focus in on our TTL values. So we've got some examples down the bottom here. So you can set a IP header's TTL value in software. So if you wanted to make sure that this packet does not get off the local network, you could set the TTL value to 1. So if that packet was to go through a router, that'll be decremented 0 and drop. So it would not leave your local area network. Again, you could kind of play around these values. You wanted to ensure that a packet didn't leave the campus. If you set it around about 4-ish, very much depends where you are on the campus network. So if you want to avoid the packet going out to Janet, you just set the TTL value to the max number of hops within the campus, roughly 4-ish, and then it will time out. It will reach that count of 0 within our network and will not be allowed to go out onto Janet. Alternatively, if you want your packet to traverse the world, as we saw with the traceroute lab, the traceroute command is typically limited to 30 hops. That gets you most places. Sometimes you need a few more, but definitely less than 64 normally, unless things have gone wrong. And with that number of hops, by that number of jumps between networks, we can pretty much get to most places. So typically you'll see TTL values initialized to the value 6428, or if you just want to make sure it does get to where it's going to, you can set it to the value 255 because the TTL field is a 8-bit value. Right, and so in the labs we have used the ping command as you see at the top here, so ping a name or ping a fully qualified name, and obviously they're stored in our hosts file and they work perfectly fine. So you can ping a name or ping a number in the lab and they will work fine. However, you can also add some addition parameters. So we also saw a case where we added the -c, how many times ping will send a packet out onto the network. So you can hear, if you set it to 2, it will send 2 ping packets out onto that network. But you can also set the time to live value. So in this case here, you can set it to the value 1. And if you do that, can you ponder why the first one here does work and the second one doesn't work? So in these examples here, I'm pinging on the 172 network. So I'm on desk 85 here, for example, but imagine that number there was your desk number. So you're pinging here one IP address and that will work fine. But if you ping this other IP address, it won't work. Can you spot why that is so? Equally with the ping command, we can also use the -s and the -m flags. So typically the payload of your ping command will just be padded with random characters to make up to the minimum packet size, but you can also specify a particular size for your ping packet. So here I'm specifying that it'll be 1500 bytes, and this is the machine I want to ping. So again, it'll just pad it out with random rubbish. So this command here will work perfectly fine, but the one below it won't. So a little bit of research and thought here. What does the -m flag do? So have a look on the man page. So within a Raspberry Pi terminal, type in the command man ping and you'll see all the options associated with the ping command. So why does this one not work? So again, one to ponder and one we'll go through in the lecture review session. So fingers crossed, touch wood, we're happy about what the TTL field does do, but to see it in action, we'll deliberately create a network loop. So this example here we're going to construct is a good example of why we need that TTL field. So what we're going to do is we are going to ping a IP address that doesn't exist on our network. And by misconfiguring our routing tables in Pi 1, Pi 3 and the router, we can set up a loop where the packet just keeps constantly looping between these devices and doesn't actually get to where it's trying to get to. So the network scenario we're going to create is Pi 1 is going to ping the IP address 10.200.0.1. That will then be forwarded onto our router, our MikroTik router, which will then forward it on to Pi 3. Pi 3 will then forward it back to the router, so you can see now it'll get stuck in this loop. And if we didn't have a TTL field, obviously it gets stuck in there forever. But every time it goes through the router here, it will be decremented to 1, and obviously eventually it'll get down to 0 and it will be dropped. That's what we want to do, and we do that if we set up our system with the following routing tables. So this is the routing table for Pi 1, the router, and for Pi 3. So can you have a look at these, and can you spot why, if Pi 1 was to ping the IP address 10.200.0.1, we'd end up with that network loop? Why we'd end up with a packet getting stuck between Pi 3 and the router? And as always, we will look at the answer to this in the lecture review session. More demo. So yes, this lecture here is a lot of show and tell. So within our Raspberry Pi system, we have a switch and a router, and our router is this beastie here, our MikroTik router with 4 ports that you can see on the front there. So the first 3 are connected to our Raspberry Pi, and this 4th one is free. So within that device, we can set that one up with different routing rules, offering different services to the network. So within here, this is set up to be our DNS server, for example. So how do you set those up? And we'll have a look at that one in the lecture review session. So typically nowadays, your routers will have different interfaces. They'll have, as you can see here, a web interface. So across HTTP, you can connect to the MikroTik and set up its internal configuration using this graphical interface. But more traditionally, you would use SSH and Telnet. And then you have to use different command line tools to, again, do the same operations. And we'll have a quick look at that one in the lecture review session. Okay then, so using one of these interfaces, we can configure our router, set up the routing paths manually if we so desire to ensure that our packets are correctly routed from one network to the other networks. But as you can imagine, that's an awful lot of work. What we really want is a protocol to do that, and that's what we have. So the one we're going to look at first is RIP, so the Routing Information Protocol. Yes, a very dated protocol, as you can see here, goes back to 1980s. However, the advantage of looking at this one first is a very simple protocol to understand. Later protocols like OSPF, Open Shortest Path First protocols, a little bit more complex to set up and a little bit more complex to understand, whereas RIP, nice and simple, and it gets the point across. So what we're trying to do with our protocol. As always, if you want a little bit more information about this protocol, we have an RSC, so 1058, so do have a look at that one. So basically, RIP is based on a distance vector, so each router will have a distance vector that defines the shortest path between itself and another router. So the values within that distance vector are measured in hops, so how many other routers do I need to go through to get from point A to point B? And we limit those values to 15 hops. So a hop value of 16 is unconnected, for example. So these distance vectors are broadcast by each router every 30 seconds or so you can configure that value. It's not hard fixed. You can vary that one, how frequently you want these packets transmitted. So as they're broadcasted, that will be a UDP packet. So they are broadcast onto your local network, and everybody, even if they don't want to know about routing, don't want to know about distance vectors, have to process these packets. But by using this mechanism, our routers can learn about other routes. They can learn about shorter paths to other routers, to other networks. They can learn about if some connections go down. So if a particular route becomes unavailable, maybe someone cut the cable by accident, they can update their distance vectors. They can update their internal routing tables from these broadcast packets. So the routers on the network can learn from each other how to get to different points, how to get to different networks. So to see that one in action, tricky one to kind of show graphically. So this diagram do take with a pinch of salt. So what I have got here is a simplified view of our network. So in this diagram, we have got 4 routers. So router A, B, C and D. And they are connected together by these links, as you can see here. So each link has a weight, has a metric. So the smaller the value, the better. So the 9 is less desirable than the 3, for example. So what is the 9? Well, strictly speaking, it's the number of hops. So that's what RIP uses. So it's the number of routers in between you and where you want to go to. So technically speaking, I should have put 9 more blobs on this link to show that it's 9 hops from A to C. But as you can imagine, that's going to be quite a complex diagram to visualize and to draw. So to simplify that, for the purposes of this example, I've removed those. So this is a summary of the number of routers in between A and C. If you want to, for the purposes of this discussion, you can consider that to be speed. So for example, 1 would be a very fast communication link, so preferable, and 10 would be a very slow one. But do remember with RIP, the metric here that we use to assess the quality of the link is hops. So how many routers does packet have to go through to get from one point to another point? So in some respects, that doesn't matter. But technically, if we're using broadcasts, obviously a broadcast will be on a local network, and router A is not directly connected to router C. So it won't see those broadcasts directly. Those will be chained through the various routers and eventually C will get it. But I want to ignore that for the moment because it makes the explanation a little bit more tricky to describe. So, okay, so for the purpose of this discussion, we've got router A is connected to B and C. So it can see those 2 routers. It can see that the distance from A to B is 3 and from A to C is 9. Obviously, B is connected to A and C, so you can see there with a distance of 3 and 2. And we have D is only connected to C with a distance of 5. So at the beginning, that's all these routers know about. So they can update their distance vector tables with these values. And that's what we're seeing here. So here's router A, B, C, and D. So at the moment, all it knows about is what it's locally connected to. So obviously the distance to itself is always 0. So you can see A to A. So from A to A is 0. B to B is 0. C to C is 0, etc. So at the moment, router A does not know about router D. So I've obviously preempted the fact that it will learn about router D in 2 ticks, and I've added that to that particular table. But at the beginning, it does not know. It does not know about router D. So this is the distance vector for router A at the beginning, B, C, and D. So at some point, these various routers will broadcast this distance vector onto the network. It'll go, this is what I know about. These are the routers I know about, and these are the distances from me to those other routers. And it will receive those values, and it'll use those values to update its distance vector. Okay, so for the purpose of argument, let's say router A receives the distance vector from B and C. Obviously, it won't receive it from D because it is not connected to D, but it will receive eventually the distance vector from B and C. Now we can use that data to update its distance vector to see if it can discover new paths or shorter paths. So obviously the path to itself will never be better than it is, so that's always going to be 0. Then it will look at the path to router B. So it can see from router B's distance table that the distance from B to A, so from B to A, is 3. And I go, well, is that any better than I've got at the moment? No. So that will be the same. Then it will look at the distance vector from C, and it go, well, what's the distance from C to A? Well, that's 9. That's what I've got at the moment, so that one's no better. But can I see another path from A to C? So it'll look at distance vector for B. So it goes, okay, how quickly can you get to C? So they go, oh, well, I can get to C in 2 hops. And I know I can get to you in 3 hops. So there is a path from A to C that will take 5 hops, which is better than the 9 we see here. So it will update its distance vector accordingly. If we go back to our diagram, we can see that a better route would be from A to B to C rather than going from A to C, because that's only 5 hops, whereas that will be 9 hops. So that would be the preferred path. That would be the shorter path. Again, it will look through the distance vector to see what else was in there, and obviously it will discover here that there is someone called D. C in its distance vector has a path to router D, which A did not know about. So again, you can use that information to add a path to its distance vector. So C can get to D in 5 hops. A can get to C now in 5 hops as well. So the distance from A to D will be 10 hops, and it will update its table accordingly. It will then create a new distance vector, which it will then broadcast to all the other routers eventually. But obviously when A was updating its distance vector, routers B, C and D will be doing the same. So they will be receiving the broadcasts from other routers at the same time, and they will update their distance vectors accordingly. So again, we can see here that router D receives the distance vector from router C that contains information about A and B, so it will update its distance vector to include those routers. Same for router B. Obviously B again is not connected directly to router D, so it will update its distance vector with this new route. So it receives a distance vector from C saying that it can get to D in 5 hops. It knows it can get to C in 2 hops, so therefore it takes 7 hops from B to get to D. So again, if you look at all these routers, we can see they're updating with new information. They're updating their distance vectors again. So router D, I now know about A, so it knows that C can get to A in 9 hops and it can get to C in 5 hops. So therefore it's 14 hops from D to A, etc. So they basically all update their distance vectors. And as you can probably imagine, they then rebroadcast these to everybody to see if they can update their distance vectors to the shortest path. Because as we know, this is not the shortest path. So again, they all broadcast. So now C is updated with a shorter path to A. So going from A to B to C rather than from A to C. So that goes down to 5. And obviously that will be broadcast to everybody else. So they'll update their distance vectors accordingly. And now we'll see, after they've recalculated the various distances, those values being updated. So for example, this one here, it was 14 because it went from D to C to A. But now it's learned about a shorter path from D to C to B to A. Obviously now that goes down from 14 hops down to 10, so a better path. So RIP1, it's a nice simple protocol. It's fine for small networks. Well, fine. There's a few security concerns, but we'll ignore those. But functionally, yes, it's fine for small networks. It is limited to 15 hops, and as we saw with the traceroute command, yeah, that's kind of okay, but sometimes if you're traveling across the world, it does take a few more hops there. Some other limitations, as we saw in the previous example, RIP doesn't remember alternative routes. So if it was to receive distance vectors from other routers advertising other paths to the same point, it would only remember the best one with the shortest number of hops. Which is okay, but you're losing that other information. You're not remembering those alternative routes. Again, as we saw, the metric used to assess what is the best route is based on hops, and it doesn't include any information about the cost of the route in terms of speed, for example. And that would obviously be something we would like to integrate into our routing protocol. Finally, RIP doesn't carry any network masked information. It doesn't support our CIDR networks. But yeah, for small networks, it works okay. However, for larger networks, we start to run into problems. As you can imagine, for 1 or 2 routers, broadcasting a few small packets every 30 seconds or so, not an issue. But what happens when you have 10 routers, 100 routers, 1,000 routers? You can start to generate a lot of traffic. You can imagine if you have lots of routers and they're all chucking out packets every 30 seconds onto our network, And a broadcast packet has to be received and processed by everybody. Even if you're not interested in this routing data, it's interrupting machines that don't need to know about it. That can cause a problem. You're just squidging onto the network a lot of noise unnecessarily. You're interrupting various machines that don't need to know about these routing protocols because they're not routers. So to solve some of those problems, we have RIP2, RIP version 2. So again, RFC 1723 if you want a little bit more information. So this one here corrected some of the issues. So RIP1 was based on classful addressing, whereas RIP2 uses CIDR. So we have completely configurable subnets there. It also has encryption to some level, MD5 encryption and passwords to give it a little bit more security. But the key thing here is it switched to multicast. So as I say, previously RIP1 was a broadcast protocol. So everybody, even if you weren't doing any routing, had to process these packets. With these ones, we use multicast. So with a multicast address, it's not one to all, it's one to a selected pool of people. So you can set up your routers to listen on a multicast address, but everybody else will just ignore these packets, which obviously simplifies the processing for these other hosts on the network. So again, if you go back and look at the previous lecture at our classification of our classful addressing structure, so we can see that a multicast IP packet is identified by the fact that it will have 3 ones in the top most significant bit positions. So that means that the IP address has to start with 224 and it goes all the way through to 239. So that range of IP addresses define a multicast address. So for RIP2, IANA has defined that its multicast address will be 224009. So anybody who listens on that multicast address is listening for RIP2 packets. So RIP2 does solve some of the problems with RIP1, but it doesn't solve all of them. So we're still limited to 15 hops, mainly due to solve the counting to infinity problem that RIP2 and RIP1 suffer from. So to see that one in action, consider our previous diagram. So again, we've got our 4 routers, but now the link from C to D is broken. Maybe we had a digger and it's dug up our cables and it's cut the fiber optic cable that went from C to D, and now there's no connection now to that final router. So we'd like to remove that from our distance vectors because we can no longer communicate with router D. That path is dead. But there's a problem. If you go through the process I previously described, you'll see what I mean. Okay then, so here are our various routers. So router A, B, C and D as previously described. So router C will detect that obviously that cable has gone down. It can no longer communicate with router D. So it will remove the distance vector that D communicated to it from its calculation. So that column will now go. So now it will have to see if it can find a different path to router D. So the path that had 5 hops in it will be removed. So it will look at its other distance vectors to see if it can find another path to router D. So it does that. It looks at these ones here. It goes, oh, okay, router A and router B know about router D. And I know I can get to router A in 5 hops and router B in 2 hops. So I can get to it in 15 hops or 9 hops. So I'm going to take the 9. So it goes, okay, I know I can get to router D in 9 hops now going via these other routers. And obviously we know that's not true, but the way the algorithm works, it doesn't realize that. So it will update its distance vector now with that new value, and then obviously rebroadcast it out onto the network. So this distance vector will be received by router A and router B. It will then recalculate the various distances. So router B knows it can get to router C in 2 hops, and it knows that router C supposedly can get to router D in 9 hops, so therefore it will update its distance vector for router D to 11. Router A will do the same, so it knows it can get to router B in 3 hops. It knows before the next update that supposedly B can get to D in 7 hops, so its value will be again 10 hops. Now router B will retransmit its distance vector. That will be received by the other machine, so the value 11 coming in here. These routers will then update their distance vectors with that new information. C can get to B in 2 hops. It says it can get to D in 11, so that'll update to 13, and A will update its to 14. They will update their distance vectors, and again, those will be retransmitted. So you can see what's happening here. Our distance vector value is ever incrementing to infinity. So if we don't set a limit, it'll just keep counting. So within RIP 1 and RIP 2, we set a maximum limit of 16. So as soon as our hop count gets above 15, gets to 16, that route is deleted to counter this issue. So as always, we'll be using our Raspberry Pi test system to have a look at these routing protocols. So here we have our network diagram. We have our PC, we have our switch, we have our MikroTik router, and we have our 3 Raspberry Pis. And yes, I know these are the icons for supercomputers, but if you viewed them from above, then they look like a pie chart. So the bit jutting out there is a slice of pie, perhaps Raspberry Pi. So that's why I chose them. That's why I use your classical Cray 1 supercomputer icon for the Raspberry Pis. However, glossing over that, we have 4 hosts in our network. We have our PC and 3 Raspberry Pis. And fingers crossed, touch wood, you will have identified there are 4 subnets in this system. So we have a /16 subnet that all Raspberry Pis are a member of. And then each Raspberry Pi is in a separate subnet, a /30 subnet, with the router. So these are 3 different subnets connected to our router. Knowing that, time for a quick quiz. So can you identify from this network diagram how many collision domains there are and how many broadcast domains there are? And as always, we'll be looking at that in more detail in the lecture review session. Okay then, so up to this point in our test system and in our base system, we'll be using the Raspberry Pis as hosts, either as a server, a web server, mail server, whatever it may be, and a client. Typically, most of our servers are running on Pi 1, and we're using another Pi to act as the client. However, we can configure our Raspberry Pis into routers. So there's some software called Quagga, which is a fork of Zebra, which is a suite of software that allows you to implement various routing protocols. So our RIP, OSPF, BGP, etc. So just as a bit of background info, where this name came from, Quagga is a subspecies of Zebra, I think now is extinct, from South Africa. So the original router software was called Zebra, so a fork off Zebra is a Quagga. So we can use this software on our Raspberry Pis to turn them into routers. So now our network diagram looks like this. So from this point of view, each Raspberry Pi is now a router. So in some respects, the top level view has not changed, but if you look inside each of these Pis, you will see that I have renamed the loopback interface to a 10-dot network. So now each Raspberry Pi, each Quagga router, knows about 3 different networks. An externally visible 192 and 172 network and a secret internal 10-dot network. So in our system, we have all these different subnets. Some are externally visible and some are hidden within the Raspberry Pis. So by using our routing protocol, we can communicate across that network now to everybody, all the different routers, information about all these different subnets. And fingers crossed, touch wood. So when we turn all these routing protocols on, everybody will discover all these subnets and therefore know how to route packets to them. And that's what we'll be doing in one of our practicals. As I said, RIP is definitely a dated routing protocol, not commonly used now. So what has it been replaced with? Well, it's been replaced with OSPF, so Open Shortest Path First routing algorithm. As always, there's RFCs on that one if you so want to. Do have a read around on those. And that's the one we use inside the department. So RIP and OSPF are interior gateway protocols. It's a protocol used inside your network, inside your building. It's a protocol that allows the routers in your buildings to talk to each other to discover the paths between themselves to connect all your various subnets together into your network. So to get over some of those limitations of our RIP protocol, OSPF uses a different routing algorithm. It uses a link state routing algorithm, which allows you to pull in some other different metrics when deciding which is the best path. So the speed of those links, for example, which does make it a better routing algorithm. So yes, when we look at its advantages and disadvantages, we can see it overcomes most of the limitations associated with the RIP protocol. So no limitations on hop count, supports our variable length subnet masks, our CIDR networks. Like RIP2, it uses multicast, get rid of those broadcasts. It supports authentication and all those good stuff that was missing in some of our RIP protocols. But as always, this isn't cost-free. So because the routing algorithm is slightly more complex, it needs more processing time to calculate those paths. And obviously that will come with some memory costs as well. So you're probably asking, why then, Mike, why did we use RIP in the lab practicals rather than OSPF? I do confess that was made from a teaching point of view rather than a training point of view. So RIP allows me to demonstrate that transition from a broadcast protocol to a multicast protocol. So to start to introduce those ideas and see those in obviously our Wireshark captures. To start to think about what types of communication we need on our network and the costs associated with a broadcast where everybody has to process those packets. And I confess I've played around with OSPF, but I haven't really used it in any major networks that I've built. From that messing around, I found it was a little bit more difficult to set up than RIP. I found RIP was pretty much a fire and forget protocol. You turned it on, it just worked. And OSPF just needed a little bit more explaining from a teaching point of view and a little bit more setup. So from that teaching point of view, RIP allowed me to get those concepts over more efficiently. So that's the protocol I went for in the end. However, once you got the basic skills, once you understand what RIP does, it's only a short skip and a jump to get to OSPF. So yes, definitely OSPF is the one you need to know if you are creating any model networks. And at the bottom there, we have a nice link to a video which talks through some of the added complexities of OSPF. So yeah, do have a look at that video. Definitely a good one to watch if you're moving into the network space. Another protocol to be aware of, but unfortunately beyond the scope of this module, is BGP, so our Border Gateway Protocol. As always, RFC for that one, 1105. And whereas OSPF was an interior gateway protocol, BGP is an exterior gateway protocol. So what does that mean? Well, this is the protocol used by the routers that connect our autonomous systems together. These are the routers that live between the networks of networks, our autonomous systems that make our internet. So these edge routers exist at the boundaries of these networks and are the things that connect together these bigger networks to form the internet. So as you probably guessed, the decisions here of how we route traffic across different networks owned by different people, the priority of which route we take, which path we take, is different to the decisions you make inside your own building. So inside your own building with your interior gateway protocols, you own everything. Here, that may not be the case. So deciding the best path between these networks is tricky. As I say at the bottom there, here be dragons. So those routing decisions are obviously, perhaps you have to pay to use somebody else's network, or there's limitations on speed and capacity. So lots of other decisions to be made. So yeah, we need a different protocol. And at the bottom there, there's a nice link to a video that discusses the joys of DNS and BGP. I thought that's quite a nice video. So yeah, do have a look at that one as well. But for the purposes of this module, it's just an introduction networking module. I'm afraid there's not time to look at this one in any depth. So we come to the end of discussion about our network protocols, our layer 3 protocols. Key thing to take away from there, obviously, what is IP? IP version 4, IP version 6. Nowadays, we're heading towards IP version 6. But IP version 4 is still out there. It's definitely still used. And as I always say, it would be a brave person indeed to turn off IP version 4, turn off that protocol. With the amount of legacy systems out there on the internet, to do a cold switch to IP version 6, yep, definitely a lot of things wouldn't be happy. So I think we're living in the world of dual stacks for a significant amount of time. But yes, definitely the backbone of our network, if it hasn't already switched over to IP version 6, yeah, that's coming, definitely. But from a home user point of view, not so sure. But yeah, we will see. We will see. I'm sure at some point it will happen. So we looked at fragmentation. So we saw how IP version 4 can break down those bigger transport layer segments into smaller MTU sized packets to travel across our network layer. That ability to obviously fragment bigger packets into smaller packets is a very nice thing to have, but I do believe there's some security issues with that one. If you start to spam fragmented packets to a router, I think you can cause bad things to happen. So not a desirable thing necessarily. So in the practicals, we'll have a go at configuring our routers. We'll configure that MikroTik router to connect to another MikroTik router. So you'll set up some routes, you'll assign some IP addresses to that router. But they are tricky things to use, and you only really get that experience from doing, as always. For this introduction to networking module, we don't really have the time to go into routers, router configuration, router setup, routing protocols in any depth, really. That's a module in its own right. So I'm going to leave that one to you if you're interested to do your own background reading. But as far as the assessments and the practicals, I'm not expecting you to have any in-depth knowledge of these protocols. Okay, so we have finished our network layer. Now we will push down our protocol stack again to answer these unanswered questions. So, okay, we can route our packets across the internet using IP, but how do we transfer those data bits across our local network, our LAN? The answer to that one we've already discussed in the first lab. We use our Ethernet cables and we use that Ethernet protocol. But what is the difference between a logical address and a physical address? How do we identify our hosts on our network down in the next level, down in that link layer, down at that data link level? And as always, that's what we will be looking at in the next lecture. All right, then, I'll catch you then.